Hello everyone and welcome back to the second session of Warwick Data Science Society's Into the Tidyverse course. So in this session we're going to return back to the start of the data science pipeline, and that is importing data from external sources into R. We're also going to have a bit more of a look at some more advanced plotting techniques such as line plots. But to start off, we're going to have a quick recap of the stuff we looked at in last session. So the main thing we looked at was how to create a basic scatter plot, and through that we learned the general framework for how to create a ggplot. And that looks something like this here. So the basic structure, we start with a base layer, and that's created by using the ggplot function. So create a base ggplot, and then inside of the brackets we put in the data set we want to use throughout our plot. We then follow this by a geometry function, so geom underscore something. And we connect those together using a plus, which is the symbol for adding a layer to a plot. Inside of the geometry, we then put aesthetic mappings. And so these are done inside of the AES function, short for aesthetic. So aesthetics are any physical element of a geometry, say their X or Y coordinate, their color, shape, size, various things like that. And we map variables in our data set, the one defined at the top, to aesthetics of our geometry. If we want to manually set any properties, then we can put that outside of the aesthetic function. Otherwise, strange things will happen. We saw an example of that in last session. We also saw how to facet a plot, and this is a way of taking a single plot and breaking it up into multiple subplots. And the reason we would want to do this is to allow more complexity visualization without overburdening the different types of aesthetics we have available to the point where a plot becomes confusing. And so we saw two ways of doing this. We could use facet wrap to facet by a single variable that would wrap around after a certain number of columns, or we had facet grid, which allowed us to facet by one or two variables in the row and column directions. And we also had a bit of a look at how we can work with data frames to learn a bit more about them. We saw head and tail for getting the top and bottom rows of a data set respectively, summary for numerical summary statistics of each column, str short for structure for the general structure of a data frame, and then the $ and double square brackets for accessing single columns. And finally, we saw how to get help about a data set, or any function in fact, by using the question mark before an object's name, and that brings up the help files inside of RStudio. So if you want a recap of any of that, you can look at the last session or look at the presentation for kind of a briefer overview. So before we get into the main body of today's session, which is importing data, there are a few things we skipped last time in order to get straight into kind of the exciting stuff, which is plotting. So we're now going to take a moment to go back to the basics and get some of the more fundamental R knowledge that will be important for the rest of the course. And so that's what we're saying here. We've missed out on a few fundamentals. It'll be good to go back and look at those, as well as looking at a few tips and tricks that we can use inside of RStudio to make coding R a bit easier. Okay, so we saw last time we can use R as a basic calculator. So we could do, for example, in the console 1 plus 3, that gives us 4. We did multiplication with the asterisk and exponentiation with the caret symbol. So 7 to the power of 3. We can go a bit more beyond that. So for a start, R understands bidmass and brackets. And so the order of operations, it gets that. I can do 7 plus 3 times 2, and it will do the 3 times 2 first, as it should, and then add on the 7 to give 13. There are a few other functions we might want to use. So there are the trigonometric functions. So sine, for example, what is the sine of pi on 2? You can see we also have this, this constant pi here, because I'll show you that one first. So we have pi here, which is just the number pi. And then we can take the sine of pi on 2. If you remember your high school trigonometry, this should have the value of 1. And we have all the other ones we might care about. So cosine, that's about 0. We have tan as well. We also have the inverse ones. So what are they going to be? So we have a sine and a cos. Those are the inverse functions. as well as the hyperbolics if you care about those. We also have the square root function, so sqrt. That is going to square root a number. So the square root of 100 is 10, as we would expect. And we also have functions for computing logarithms. So we have this log here. This is by default a base E log, so a natural logarithm, often referred to with ln. So the natural logarithm of 9 should be 2 point something. Or we can have base 10 logarithms by using log 10, base 2 logarithms with log 2, or generic ones using log b. That will let you choose the one that you want. Okay, so that's a few bits of maths there. So let's talk about these things called objects. So an object is a way of storing a value in R for later use. And so think of this as a way of giving R some memory. And so in other languages, this would be called a variable. And I might end up using the word variable by accident, but in R, you typically refer to these as objects. And so it's simply a way of labeling a piece of data, say a number, some text data, or a whole data frame, just giving that a name to refer to later. And in R, we create an object by using this symbol here, which is a less than sign and then a hyphen. And this is known as the assignment operator, and it assigns a value to an object. So in this code here, we take the right-hand side, which is 3 times 4, so the number 12, and then assign that to the object x. And so now x points to that bit of data, 12. And so whenever we use x in the future, it's going to have a value representing 12. For example, take a different example. If I set x to be 6 minus 2, so do 6 minus 2, and then assign that, so less than, and then a hyphen to x, I can now use x in my code. I can maybe times x by 3, and this x value represents whatever value we last assigned to it. If we replace the assignment, say x has the value of 9, then if I now do x times 3, we're going to get 27. It remembers the last value that we assigned to it. And so the general format of this is a name for the object, and then we assign it a value. And that can be a direct value, say a number, or some text, or it could be a computation like we had 6 minus 2 before. And so an object will retain its value as long as we don't close our studio, we don't manually delete it, or we don't overwrite its value. So what we did there when we set x to be 9, when it was already having a value of 4, is called overwriting. We overwrote its value, giving it a new one of 9. And so by doing that, we lost the original value of 4. And so we can see a list of all variables we have defined, sorry, all objects we have defined. You'll see I'll keep mixing those two up, but they mean the same thing, really, over in the environment here. So this might be in a different place for you, but one of these tabs should have an environment tab you can click on, and that will show you, if I define maybe a new variable, y with a value of 3, that will appear in my environment there. And so many languages like Python or JavaScript use an equal symbol for assigning a value to an object or variable, and R will accept this as well for consistency. But it's generally not advised to do this because it can cause issues later on when you're doing more advanced R coding. And also argue that this symbol here makes more sense. This evokes ideas of the equal symbol in maths, when really there's no equality going on here. We're assigning a value, kind of passing that with an arrow into that name on the left. That makes a bit more sense. So we tend to use this symbol. And so if typing this out is a fuss, you can use the shortcut of Alt minus. So if I go into here, so Z and then Alt minus, that will give me that symbol and add a space. But really it's 2 characters, so it's worth doing just for clarity of code. Okay, so the rules for defining a variable name. So objects must start with a letter, and they can only contain numbers, letters, underscores, and periods. So you can't, for example, have a hyphen in a name. That will confuse R because it can't tell the difference between a hyphen and a hyphen being used for subtraction. And so it's good to have a name that is descriptive and try to follow the same naming convention as in the rest of your code. So something like, obj for like object, and that's going to have the value of 1729. This is a really bad name because it's hard to tell what object refers to. It's just a very generic name. But if I called this my fave number, we can now understand what data is represented by this name very easily. And you might be thinking, well, yeah, that's an awful faff to write out every time. But thankfully, because we're using RStudio, which has a load of helpful features, one of those features is auto-completion. And so if I start typing out a variable and then press tab to say, hey, give me some suggestions, it will actually auto-complete that for us. And the reason it did that was because there was only one object or one kind of so object or function or anything in the language that began with my underscore. If I created a new variable, which was my fave word, and that would be quick exotic, if I can spell that correctly. If I now do my underscore, there's now multiple options, and I can use the up and down arrow to choose between those. And if that thing doesn't appear, then you can just use the tab key to make it appear. And once it has appeared, you can use up and down, press tab to select the one that you wanted. So don't worry about long variable names. It's good practice to have clear and descriptive names, and that way it's a lot easier to follow what your code is doing. And so that's what was mentioned here. Do be careful though. Object names in R are case sensitive and are intolerant to typos. So if I have my fave number, or if I have missing the underscore here, it will say object not found. And that's just R's way of saying, hey, this thing you're asking for doesn't exist. So just be aware of that. You have to be exact with the names that you use. Okay, and so one more thing to mention is this notion of code history. So you might have seen me doing this thing where I'm going back to old code. And I'm doing this by using the up and down arrows on the keyboard. So I can use up to go back to old code, and then down to go back to more recent code. And for a full view of this, I can open the history pane, or the history tab inside of RStudio. That gives me all of the commands that I've ran in this session, going from the most recent at the bottom to the oldest at the top. If I pick any of these, I can then press to console, and I'll put it across into my console like that. Or to source will put it into a script if I have that open. I'll mention a bit more about scripts in a second in case you haven't watched our bonus video between the first and second session. Okay, so we'll also talk a bit about what functions are. So I've used this word a bit already, but now let's define it properly. And so R has a lot of these things called built-in functions. And a function is simply a way of getting R to do something. You can think of these as the verbs in the R language. And so the general structure for a function is something like this. So a name of the function, and then brackets. And inside the brackets, we have the options that we supply to the function. So basically, kind of the adverbs of this verb. It's kind of how we should run that function. And so these are often of the form the name of the argument, the name of the input, and a value. And there could be none of these, one of these, two of these, or any number of those. So an example of a function is seq, which is used for generating regular sequences of numbers. So for example, we can use seq and use the arguments from set to 1 and 2 set to 10. And that's going to create a sequence from 1 to 10, something that looks a bit like this here. But for many functions, we actually don't have to name our arguments. We can simply put in values, and R will have a sensible guess at what those values represented. And so there is kind of definitive rules of when we need to use named arguments and when we can avoid it. But generally, a rule of thumb is if the arguments seem obvious, you can get away without naming them. So if I'm generating a sequence, quite an obvious thing I'll need is kind of from what to what. That's kind of the definition of a sequence. And so I can get away with not naming from and to. Actually, it's the same when it comes to a ggplot. You might see in places ggplots being written like this. So data equals mpg. Let me load up the tidyverse before we get started, or we'll run into some errors. Plus geom_point mapping equals AES. And then X is highway, Y is city. So we can run that, and that works the same as normal. So here, this first argument, the data argument of ggplot, that actually can be named. It has a name of data. But because it's so obvious, obviously if we're creating a ggplot, we want to have some data to be used, we can get away with missing out that name. And same with here, like it's obvious that a geom_point should be followed by an aesthetic mapping, and so we simply miss out the name of that argument, and that works fine. There's no harm in including them if you want to. And we'll actually see, I think, in this homework, or it could be in the last homework sheet, examples of when we can actually miss out X and Y in these plots, because again, they're fairly obvious parameters. We get the same plot still. The general rule of thumb is if they seem like obvious arguments, or we're using them a lot of the time, you can probably miss the name out. And if something goes wrong, well, probably put the name back in. Okay, so I'll now just quickly mention 2 or 3 common issues that you might run into while coding in R. The first I mentioned, I think, in the live session last time, but I'll mention it properly here, is what happens when we don't properly complete a line. If I say open some brackets and I do 3 plus 4 and then forget to close the brackets and I press enter, nothing's going to happen. And you'll see that my prompt changed from a right arrow to a plus symbol. So a right arrow means I'm ready for new input. So R is in a stable state and wants a new line. Whereas the plus means I'm still waiting for more information. So this is not a complete block of code yet. I need more and then I can run it. And so what's missing here is that second bracket. If I put that in, sorry, I deleted that one first. So you can see I can add lines here, does nothing, it's still waiting for the bracket. As soon as I put that bracket in, I press enter, everything's complete and it will run that code. So if you see a plus like that, you're probably missing something. If you get yourself stuck in a state and you're not sure how to get out, then you can just use the escape key on the keyboard to cancel out whatever you were running above. So another thing we mentioned earlier was if you have a typo in an object name, you'll get an object not found error. So if that happens, just make sure you've spelt things correctly and have correct capitalization. And if you're ever unsure of what arguments a specific function takes, you can look at the help file. So for example, if I want to look at the help file for SEQ, I run this and I'll see. So here it is here. This is the main documentation. So it has these arguments here, so from and to, and anyone that's set equal to a certain value, that's its default value. So this is saying if I do a sequence and just put 2 equals 10, the default for from is going to be 1. And so I'll get a sequence from 1 to 10. And I can overwrite that from, if I want to, say from 3 to 10. And we'll get something like that. You can use the documentation to give you an idea of what sort of things can go into a function to give you control over it. Okay, so that's all of the kind of basics. Obviously covered very quickly, and we'll see some more examples in the exercises in the homework to kind of actually get that in your head and kind of start remembering all those new techniques. But for now, we're going to move on to the main body of today's session, and that is importing data. So let's return to our map of the data science pipeline. So last time we were looking at visualization, somewhere right at the end here. And now we're going to go back right to the start and look at importing data. And hopefully now that we have something to do with the imported data, it's going to make a lot more sense to be importing it. I can see here that there's mention of this weather data set. I'll get that removed from the slides once they go up. This is from an old iteration of the course, so don't worry about that. That won't make any sense. Okay, so we're going to use a package called readr for importing data into R. So this is, again, another package that forms part of the Tidyverse, and it's used for importing data from a wide variety of formats. So from flat text files and from many other types. And so readr is kind of designed to bounce between both speed and ease of use. And it's designed to be very consistent. You can import various different file types, and it has the same sort of syntax for all of those, which is very nice for learning things quickly. And so let's start with importing a simple file, and then we'll look at the variants we can kind of do in this reading function to kind of read some more complicated types of data. So the type of data we're going to be importing is known as a CSV file. And so CSV stands for comma separated value. And so it's basically a file in which every row is one observation of data. And then the values, the different fields and columns in the data set are separated by commas. Hence, comma separated value. Common, I guess I'll fix that typo too. And so the reason we're looking at these first is because they're probably the most common data storage format on the web. And so it's quite easy to get data in this format. If not, if you have, say, an Excel spreadsheet, well, Excel can export to CSV, and so can a lot of other formats. So even if you don't have CSV data, it's probably possible to convert to that format. And so the idea is, each row is its own observation, and then commas separate the values. So here we have a header at the top, so earnings, height, sex, education, age, and race. You can see in the first person, their earnings is 50,000, comma, then their height to a stupid number of decimal places, comma, their sex, comma, their education, and it carries on like that. So it's a very dense data structure, but it's a very popular one, so it's worth knowing about. We can see here we have a header given the column names, but that's not always the case. So one of the scenarios we'll have to consider is what if we don't have that header, but we'll get to that later. And so to import a CSV file, you can use the read_CSV function, and that's from the readr package. So to get access to this, we just have to import the Tidyverse with library Tidyverse. So the first argument is the most important one, and that's the path to where the data set or the data file you're trying to read is located. And so this path is a relative path. It's based on something called your current working directory. And so think of your working directory as your home. It's where you're currently standing, and everything is relative to that. And so let's have a look over in RStudio here. Well, first, let's have a look at my file system here. So I am in the into the Tidyverse course on my computer. And inside of there, we have a resources folder, session 2, and data. And so there's a few data files in here that I would want to import. If I have a look at my working directory, I can do that with the getWD function for get working directory. We can see that I'm in my home, Tim, documents, the society teaching, into the Tidyverse. So that's this folder here. And so any path I give to import something should be relative to this. If I want to read in, there was people.csv inside of here. So that's going to be, I'm into the Tidyverse. So inside of there we have resources, and then session_2, data, and then people.csv. So read that in, I get this file here. And so this is the imported file. That worked nicely. But maybe I don't want to write out this massive path every time. And so what I could do, I could set my working directory to be this data folder. I can do that by using session and set working directory and then choosing a directory. So we're going to go into resources, into session 2, into data, Actually, no, let's just put it in session 2. We'll open this here, and it gives us the command that we could have ran to get there. And that's setWD, so get gets it, and set will set it. And so now everything is relative to this session 2 folder here. So if I try to run this, I get an error saying this doesn't exist. Well, it doesn't exist in the current working directory. Instead now, I'm already in session 2, so all I need is data/people.csv. And, oh, I didn't like that. Why didn't it like that? So I'm in, oh, I did put myself in the data folder. So you can see I set my working directory, I put myself in session 2 data. So all I need now is people.csv, because I'm inside of the data folder, which has that. So it's a confusing idea. The safest way to do things if you're confused by that is to set your working directory to wherever your data is, and then you can just import it with the name and not have to worry about paths, just like I did there. So that's the instructions for that. Okay, and the command we use is read_csv. So you can see here I'm running this from just outside of the data folder. So I'm going to put myself inside of that just so these commands are consistent. So inside of session 2. There we go. So I'm now in session 2. And so we can read the CSV file, read_csv, and the path to the data. We put that in as text data with quotes. And then we assign that with this assignment operator to some object, say people_df, so people data frame, to store this for later. If I take that and I run this, we get a new object in our environment, which is this data frame here that we just imported. So 1,192 rows of 6 variables. So we can see that in the environment on the left for me, might be somewhere else for you. Okay, and so we get some messages outputted just saying what column types were found in the data set. And then we just assign that to an object. It's important not to confuse readar's read_csv function with the read.csv function, which comes included with R. So read.csv is similar to read_csv, but it's not as efficient. It's got a slightly clunkier syntax. So make sure you're using the underscore version, which comes from readr. Okay. And so once we've saved people.csv in an object, we can now type out its name, and R will go, okay, yeah, I remember you assigning that the value of the imported CSV. And so when we run that, we get the output printed out, or at least just the first few rows of it. You can see we have all those various columns there, and there are 1,192 rows of that. And actually, it's also worth mentioning how quickly it imported that. Like, you didn't even see, it didn't take time, that was instant, compared to Excel. Might lag a bit opening this, especially as you get into the tens of thousands of rows, but yeah, R can handle these big files a lot better than Excel can. So that's another pro of using R over Excel. Okay, so we'll see here that when we print out people_dataframe, that the first line is a tibble. And so it's worth talking about what a tibble is. And so a tibble is just a standard R data frame. So R has this thing called data frames, which are used for storing data, like data sets. But the tibble takes a standard R data frame and adds a few features to make them a bit easier to work with and to display a bit more prettily. So for example, a tibble will limit how many rows and columns are printed out. So if I pick something that is not a tibble, so there's a data set called iris, and this is not a tibble, this is just a normal data frame. We'll see this prints out the whole data set. Even if my console is really narrow, it'll print it all out and put it, all messy like this. So not desirable. Whereas a tibble, like MPG is a tibble, will only print out the first few rows. And if I print it out with a very narrow console, it'll just print out what it can fit, and then follow that by, oh, there's 5 more columns, here's the names of those. So it just prints out everything a bit prettier, and also gives you the column types at the top. So they really are, basically the same. And if I look at the class, which kind of defines what type an object is of MPG, we'll see that it is a data frame with just this tibble and tibble data frame stacked on top of it. So it still is a data frame, behaves the same, just prints out a bit nicer. And we can convert a dataset into a tibble using as_tibble. So for example, we saw the iris dataset here. That is not a tibble. But if I do, say, iris_tbl is going to be as_tibble of iris. That's going to take the iris dataset. As_tibble is a function that converts a data frame to a tibble. And then we assign that to iris_tbl. And so now if I print out iris_tbl, this is now a tibble. It prints out a lot more nicely. And I could have ran something like this, which would replace the built-in iris with the tibble version. But I might not want to do that, just so I can get back to the standard iris one at a later point. Although, if we were to restart R, the iris would default back to its standard state. So don't worry about losing that permanently. Okay, so we're now going to look into some more advanced behavior of reading CSVs to handle some more kind of some edge cases. But to do this, it will be helpful to be able to read CSVs directly from inside of R rather than having to mess with CSV files somewhere on our file system. And so to do this, we can read a CSV in what's called an inline CSV. So whereas before, when we did something like, if I scroll up, we did read CSV and then a path to a CSV. readr will actually let us put the whole CSV data inside of these quotes here. So if it recognizes a path to a file, it will open that file. Otherwise, it will try and read it as data itself. And so this is really important for creating reproducible examples and for testing small bits of code, because the data itself is contained in our code rather than having to supply a separate file that people are going to need to test it with. So for example, we can run read_CSV, and then rather than putting a file path, we literally write out a comma-separated value file. Here are our headers separated by commas, and our values separated by commas too. So 3 columns and 2 real rows. And if we put that into read_CSV, then the output we'll get is just a tibble, as we would expect. So if we'd have taken this and put this into a file, read that file in, it's the exact same as reading it in directly inside of here. And this is called reading an inline CSV. And so from now on, we're going to be using those inline CSVs just to test out some of the other parameters in readr for handling edge cases of reading files. Okay, so the first thing we might want to do is to skip a few columns. So we saw in the previous examples that by default, readr is going to use, or read CSV, I mean everything in readr to be exact, is going to use the first line as the column names. But it might be the case that our dataset starts with maybe 5 lines of just attributions or acknowledgements or just general description of the dataset. We don't want to read those in as part of the data. And so there's 2 ways we can avoid reading certain lines, and that is using the skip and comment parameter. These are just extra inputs that we put in to any readr function, so such as read CSV, to control its behavior a bit more fine-tuned. So the skip parameter is going to be a number. It's going to specify how many rows to skip at the start of the CSV before starting to read data. So if we have a CSV file like this, so the first line of metadata, the second line of metadata, and then the data actually starts here with X, Y, Z as the headers, 1, 2, 3 the values. We can skip these first 2 by, after either our inline CSV or the file name, having a comma, and then skip equals 2. And so this number could be any number, that's just how many lines of code we're going to skip. We skip those first 2 there, and then that gives us this tibble here with just the x, y, z as the headers, and 1, 2, 3 as the values. And so another parameter we can use, fairly similar, is the comment parameter. And that's used to skip certain lines that begin with a certain character. And this is a character that's going to represent a comment line, so a line that's not data, but just used to comment the data and give more information about it. So an example comment symbol might be a hashtag. There's various others that could be used, could be 2 slashes, whatever. But if we want to ignore these, anything beginning with a hashtag, we set comment equal to the hashtag character. And so that's going to ignore any line beginning with that symbol. And so we just get x, y, z and the numbers 1, 2, and 3. Okay, and so in this example here, we had the column names in our data set, but it might be the case that we're given data where the column names are missing or they're included somewhere else. And so we need to be able to handle both of these cases. We can handle both of those using the col_names parameter of read_CSV. And so there's 2 options we might want for this. The first is if we don't have the column names in our data set and we don't know them at all. And in this case, we'll set colnames equals to false. That's false in all caps here. So R has this kind of built-in special value called false. There's also true. If you try and do something like true without the all caps, we'll get an error. So it's false with all caps there. And so what we're saying here is we don't know the column names. The column names are false. And so we'll just start reading from the first line as if that's data, and then make up some column names. And those are going to be generic names, x1, x2, carrying on in that fashion. So here we just have the data, colnames equals false, and so we get generic column names and then just put the data in. If we ran this without colnames equals false, then this first row 1, 2, 3 will be read as the column names, which is not what we wanted there. We wanted that to be all the data. So it may also be the case that we know what the column names should be, but we just don't have them in the data directly. Perhaps there's a separate file giving the column names. In this case, we can set column_names equal to a character vector giving the column names. And we create this using this C function here. I'll explain more about this just in a moment. We use the C function, and then inside of that, we have each of the column names as text, so using quotes, separated by commas. So here the column names are X, Y, and Z, and those will be used to fill in the column names, and then we'll start from the top here, reading data. And so we get something like this. Okay, so I just mentioned vectors. What are those? And so vectors are a very central idea in the language of R. They're just integral to working in R. Essentially, all they are is a collection of elements that have the same type. So you can have integer vectors, which all contain integer whole number values, character vectors, which contain text or kind of text characters, or double vectors, which contain kind of numeric decimal values. And there's many different other types you can come across. And so we don't have to worry about the type too often. All we have to know is how to make one. And we do this using the C function, which stands for combine. So combine these values together into a vector. For example, we can use C on the numbers 1, 4, and 9, all separated by commas. And this creates a vector of 3 elements with the elements 1, 4, and 9. We then assign that to the object X. So by running this, we create an object X, where it's X, that has those values. You can see here, whereas like before Y and Z are just a single value, here X is a numeric vector with elements 1 to 3 with values 1, 4, and 9. And so R is very beautiful in a way that it will apply most mathematical operators element-wise on vectors. So normally in like the mathematical definition of a vector, you can't take the square root of a vector. That doesn't really make much sense. And so what R will do is go, okay, well, you must mean take the square root of every individual element. And so R will do that. If I try to square root x here, it will square root each of 1, 4, and 9 to give 1, 2, and 3. And this is really elegant. So like in a language like Python, we'd have to kind of do a manual loop through the list or kind of do some sort of mapping to get this. Whereas R, the default behavior is to go, well, you probably mean apply this to every element, so I will. And the same sort of thing applies for most mathematical functions. I can take the sign of this vector and I'll get the numbers or the sign of each of those inputs. In a similar way, if I have an object y here, which has the values 1, 2, and 3, I can add together x and y, and that's going to happen element-wise. I could even divide them, and we're going to get 1 over 1, 4 over 2, and 9 over 3. It's 1, 2, and 3. And so everything behaves element-wise. It's really quite beautiful. And you might want to mess around with what happens when we try to add two things together with different lengths. Some interesting stuff happens, but I'll leave that as something for you to play around with. You can have a search online if you're interested in learning more. And so we may want to access a particular element from a vector. And to do this, we use a single square bracket. So double square brackets we use for extracting a column from a data set. And we can use a single square bracket to extract a single value from a vector. And we can access these using numbers. These are referred to as indices. And generally you can think of these as like the house numbers of the data. The first one will have house number 1, then 2, then 3. If I take x and use square brackets and index 2, that's going to give me the second element, which is a 4. And so R uses a 1-based indexing rule. So basically the first one has index of 1. And that differs from languages like Python or JavaScript, where you would start with 0. Okay, so that is a brief introduction to vectors. Let's now return to talking about the extra parameters we can use for read_CSV. So in the real world, it's rarely the case that our dataset will be complete. It's often likely we're missing a few values and we'll have to represent those some way so we can keep track of them. And so there's many different ways that a missing value can be encoded in a dataset. Some people will use a dot, maybe a question mark, n/a, a hyphen. There's really like an endless number of values that could be used to represent missing data. And so we can tell readr what symbols are being used for missing values by using the NA parameter. So here we're using dots to represent missing values. And so we set NA equal to the character data of a dot. We could use single quotes here or double quotes that mean exactly the same in a language R. So if you have something like this, the dots get now read in as NA. And NA stands for not available. Basically, it's a missing value. And let's say I had multiple different symbols for missing values. So it's a dot in the column Y, a question mark in the column Z. I could use the C function to combine together multiple different character data into a character vector to say that there are multiple symbols used for missing values. Here I use a question mark and a dot. I use single quotes here, double quotes here, just to prove that they mean exactly the same thing in R. I run that, and now the question mark and dot are both read in as NA values. And so NA is a very special value in R. We'll see in the exercises a bit more about how they behave, but they basically represent any missing or unknown value. Okay, so that was a very quick run through of various different techniques for reading CSV data. But even with just these few, you will be capable of importing a very wide variety of CSV files. I put 75% here I think that's an underestimate. I think maybe 90 to 95% of all CSV files can be read using these techniques. And so these techniques can easily be used for other functions in readr. And so let's look at a few more readr functions. We have read underscore CSV2. That is for semicolon separated files. So files similar to CSVs, but rather than commas for separating values, we use semicolons. And these are often used in Europe, where a comma is used as a decimal separator. There's read underscore TSV, which is for reading tab separated files. So rather than a comma, we use a tab. And read underscore delim, which is for any form of delimited file. So it could read tab separated, semicolon, or comma separated. You just have to manually specify what character is being used to split out those different values. And all of these accept the same arguments that we used for read underscore CSV. So col names, NA, skip, comment, those can all be used in these ones as well. And so this course used to contain information about fixed width files, but we're going to skip this. I think the notes are here. Yeah, so the notes are here. You can look at them in your own time. But this was included because fixed width files were part of the old syllabus. It was a special version of the course which needed fixed width files. But in practice, they don't come up that often. And so maybe just remember that this stuff exists. And if you ever come across a fixed width file, often denoted by FWF, so .fwf, then you can come back to this and learn how to import those. It's likely you won't need that anytime soon. So we'll skip over that for now. Okay, and the final thing we're going to look at is what if we have a data type that can't be read in with these available tools. And so if we're importing kind of some more foreign data, like maybe Excel spreadsheets or data from SPSS, SAS, or Stata, we can do this directly using code, but we're not going to look at that code for now, just because it's a lot to learn and might not be relevant for you if you don't use SPSS, say. Instead, I'm going to give you a bit of a cheat to use for now. And that is the data importer inside of RStudio. So if we go into the environment and click on Import Dataset, there's a list of various places we can import data from. For example, a spreadsheet. So this gives me a graphical dialog where I can pick out a spreadsheet file. I don't think I have one here to load. And then I can then mess with a few options to kind of specify how I want to load that up. That will then generate code here, so the sort of code we'd have to run to import it. We can click import to actually do that. I guess let's give an example where we read in a CSV file. So we can read a text file using readr. We're going to load up people.csv. And then we can say, how many rows to skip and various other things. And that's going to generate code for us to kind of to run. We click import, and that's going to give us that and just display it here. We can close that if we don't need it. So you may be asking, well, why don't we use that all the time? And there's, I guess, two reasons. The first is that it's slightly limited in what it can do. So it doesn't have the full-fledged capabilities of readr or similar packages for other data types. And the second is that it's not reproducible. If we write code for importing things, then we can send that code to everyone and it will always work. But with this, we have to send them a list of instructions of what buttons to click. It's hard to reproduce, and so it's worthwhile learning how to do things in code, just so you can share your code easier or more easily with other people. So for now, feel free to use that importer just to get you started, but pay attention to what code is generated and try to remember that for next time and use the code directly, falling back to this if you can't remember. So yeah, it's worthwhile learning how to do things properly with code in the long run, but for now, yeah, it's an okay cheat for now. Okay, so one more thing we're going to look at before kind of rounding up our discussion of importing data is column types. So after data science spends about a dozen or so pages discussing column types and the parsing algorithms in detail. It's worth a read, but it's a lot of information. We do not have time for that given the pace of this course. So we're going to try and condense it down into just a few slides. Now, obviously, this will be a simplification. Look at the full thing if you want to know the exact details. So the high-level summary is that Readr uses a heuristic, so kind of a guessing framework, for trying to figure out what type each column has. And so there's various types of columns. It can be integer, it can be double, which means kind of decimal data. It could be logical for true and falses, date time, say. And Readr is going to try and guess this based off the first 100 rows. And so it's often right, but it can sometimes get things wrong. And so that might mean wrong in that it causes an error, or maybe wrong in that it imports it with a type that works, but isn't as efficient as it could be in terms of storage or the speed of working with the data frame. And so if this is the case, it's worth re-importing the data, but manually specifying one or more of the column types. And so some of the most common issues are integers being read in as doubles. So whole numbers being read in as decimal data. Decimal data takes up more space in memory and it's slower to work with. So it will be best to have integers if we know our data is whole numbers only. So factors, which are kind of categorical variables. We talked about them slightly in the first session. Those can be read in as strings, which is like text data. And again, that's very inefficient, especially if there's lots of repetition in our data. Or dates being read in, again, as strings. I probably shouldn't be using the word string here, like characters or text is a more appropriate word. So basically any text data. So to manually specify a column type for a column, we use the col types parameter of Readr. Of any Readr function, such as read_CSV. And then we combine this with the cols function, which is used for specifying column types. And so the format looks something like this. So we read a CSV, and we put a comma to start the parameters. We have the col types parameter, and set that equal to the cols function. And inside of that, we map column types to variables. So the column earn should have a type of double, which is kind of decimal data. The sex is a factor. It's categorical. There's only two levels, male and female, in this data set. And so that's a factor. And the age is an integer because we only have whole number ages in this data set. And so there's various different types we can have. They're all col_something. Col_skip will just miss out a column, not import it. Col_guess will guess a column. And then there's col_logical, integer, various other ones. The ones we'll care about mainly are logical, that's true or false values. Integer double character would be an over factor as well. And date time are for either dates by themselves, times by themselves, or dates and times combined together. And number, which is only rarely used, so we're not going to worry about that. And so let's just give an example of this running. If I was to take this and run this without the column types, let's just print this out directly to the console. We'll see that the types are all doubles and then characters for sex and race. If we do this properly, then we'll get a factor for sex, which is more appropriate because there's only a fixed number of values here. If we looked at the storage size of this, I might do this in the live session if we have time. This size is going to be a fair bit smaller than this one here. So it's worth doing just for efficiency's sake. Okay, so the last thing we're going to look at is a bit more about data visualization, and specifically looking at creating line plots. So we'll look at a new geometry, and that's geom_line. But to do this, we're going to need a data set that is more suitable for time series or kind of straight line plots. And so an example of such a data set is the orange data set. And that gives data on 5 different orange trees and their circumference of their trunk at different ages. So this is stored as a data frame. And so we're going to want to convert this to a tibble just to make it a bit prettier to work with. And so I'm actually going to overwrite the existing orange data set. but I can always get it back by restarting R Studio. So now if I print out orange, I see it's a nice tibble printing out elegantly. Something like this here, so numbers of trees, their age, and their circumference at that age. And so we can use a line plot to learn a bit more about this data set. Okay, so to do this, we're going to need to use geom_line. The geom_point was used for creating a point geometry, so literal points, dots, and a line geometry for creating a line plot. And so that's a very weird comment, but basically, yeah. So this is the plot here. So we start with a base layer ggplot using the orange data set. Then we add geom_line. And then the aesthetics, X is going to be the age, so along the bottom here. Y is the circumference, and the color of each line is going to be which number of tree we're using. So these are just columns in the data set. And we can see that ggplot is very smart here. It's going to draw a separate line for each color and give us a nice legend here, so we can see which one maps to which one. So from this we can see, yellow is not the biggest at the start, but then overtakes the second tree, and that the tree 3 is fairly below the rest for most of the time. We also add size equals 2 here. That's going to control, rather than like the size of the points in a point plot, this is the width of the lines. And so we want a width of 2 millimeters here. And so another related geometry is geom_smooth. And this is used for creating, smooth curves through our data. And so whereas geomline fits our data exactly, it's very kind of angular, kind of straight lines through our data, geom_smooth is a smooth curve that kind of averages out all the points it passes over. And so it's often advised to combine this with geom_point, or at least another geometry, so we can see the raw data points and then the summaries. And so we can do this with something like this here. So we start with a base. Actually, let's open this in R Studio. We'll put this in a script here. Oh, and I also said I mentioned a bit about scripts. So a script we can create by using File, New File, and R Script is basically a place to store our code before running it. So I can put code here, pressing Enter does nothing. To then run code, I press Control Enter, and that sends it across into the console to be ran. There's more details on that on the bonus session between session 1 and session 2, if you haven't seen that already. So we start with a base ggplot using the orange data set, and we add a smooth geometry. So we're going to have the X aesthetic is the age, and the Y is the circumference, and the color is which tree we're using. The size of the line is 2, and then we add on this SE equals false. This stands for standard error bars. So SE for standard error, that's the standard error bars, and we don't want those. If we include that, we get a plot that looks like this. It's very messy. We get these known as standard error bars. There are certain scenarios where we would like these, but in this one, it's not helpful. So we set them equal to false to remove those. So we then add a new layer. We add another geometry. We're allowed as many geometries as we want. We just add them using a plus each time. Then we have the same aesthetics and then a size of 2 as well. You get a plot like this. It's nice. So we have our smooth lines and our actual data points here. Okay, but there's a lot of repetition in that code there. So we write out these aesthetics multiple times. So we have X, Y, and color. I'm going to use col here rather than color. That's something I should mention. So in ggplot, we can use color, the full name, color, the American spelling, or col, just kind of the shortened version. Those both mean the same thing. Okay, so there's a lot of repetition there. We would like to preferably avoid that. And we can do this using what's called a global aesthetic mapping. And so these behave like normal aesthetic mappings, but are performed in the base ggplot layer. And then those aesthetic mappings are used as the default for all other geometries. So they kind of are inherited by all other geometries. So in our base ggplot layer, rather than just specifying the data, we specify the data, then a comma, and then put our base aesthetic mapping. So these will be used for the whole plot. So x is equal to the age, y is the circumference, and the colour is the tree. And those were the ones we used for both geometries there. And so now we don't have to re-specify those inside of each geometry, but by doing them in the base layer, we had them accessible everywhere. And so we're also free to add specific local mappings in a certain geometry. For example, we want to have the size of each point be set by the circumference. So we added no other aesthetics for geom smooth, just these manually set ones, so size of 2, no standard error bars. And then with geom point, we used AES to set the size to be equal to the circumference of each point. So that will inherit these ones, and then we can add on another. We could also overwrite one by giving it a new value in a certain geometry. So lots of flexibility, exactly that. Okay, so the final thing we're going to talk about before wrapping up is the different aesthetics that are available for a line graph. So we saw that we could use size here, we can use color and alpha for transparency, but we're not going to be able to use something like shape. It doesn't make sense to have the shape of a line plot. Instead, we have access to a new set of aesthetics. For example, we have line type, and this controls what type of line we should draw, whether it should be solid, dashed, or dotted, say. And so this should either be kind of a categorical variable mapped to it, or it can be manually set, either being a number or the name of a line type. Let's quickly have a look through those options. So let's take the plot here. So we have this here already, just in its uglier form. And we're going to set the line type to be also the tree. So every tree is going to have its own line type. Oh, what am I doing there? There we go. So we run that, and then the first one is solid. Then we have dashed, and then larger dashed and dotted. Those are the different line types there. So we mapped a categorical variable to the line type there. We also might want to set this manually, so we can use a number for line type. 1 is solid, 2 is dashed, 3 is dotted, I think. So here we get dotted lines there. Or we can use the name, so we could say dashed. We could use solid, or we could use dotted. And there are a few other names, and you can see a list of those by following the link here in the presentation for a full list of all the available ones. And so, not sure what I'm trying to say there. So yeah, so both, I think it should be both geometries here. So both the geom line and geom smooth also have a group aesthetic. And this is used to control how our data is separated into multiple lines. So here we can see that each line, we have one line for each tree. And so by default, the group aesthetic is taken to be the combination of all categorical variables used in our plot. So here there was only one categorical, which was tree. And so the group became our tree, and there was therefore data was grouped into each tree, and there was a line for each one of those groups. But there are rare cases, and we'll see an example in the exercises, where we don't want to use the default grouping. Maybe we even want to remove the grouping entirely. So in which case we would set group equal to -1 to do this. That's just going to ignore the group. I mean, we could actually set it to any value here. Could be any number, could be some text, whatever. But -1 is the convention. So we're not going to go into that in too much detail now. But if you have a look in the exercises, you'll be able to see an example of where this matters and where you can apply this. So with that, we'll end today's session, and we'll come back next week to talk about manipulating data to try and answer questions about the data we have. But for now, thank you for listening, and I will see you next week.